All right, everybody, we're getting ready to talk about a topic that can be rather confusing. It's black bodies, like you see here, black bodies in the radiation laws. And black bodies tend to be confusing to students because black bodies don't really exist. It is a concept that we in physics and astronomy and in some fields of engineering utilize in a laboratory environment, but it gives us an idea about stars in this case because we're talking astronomy. Stars emulate black bodies in certain ways, okay? So that's how we're going to be looking at black bodies at the astronomical way of doing it, okay? So let's get started on trying to understand what is a black body, but keep in mind a black body is not a real object, it's a theoretical object, it's a hypothetical object that we've invented to utilize in the laboratory. Now a black body, for the most part, this is not in all cases, is a mathematical model. We do have physical models of black bodies, and when I was in the Air Force, I used to utilize a physical model of a black body. But for the most part, a black body is a theoretical mathematical model of how stars function, okay? So, a black body is a hypothetical object. Hypothetical, it's not real, okay? Keep this in mind. Hypothetical object, okay? And a black body does two things. Remember, it's not real, so we make it a perfect object. There's no such thing as a perfect object. So a black body absorbs all of the electromagnetic radiation that strikes it. It absorbs. Every frequency of light that hits it gets absorbed. That never happens. This is not real world. This is idealized, okay? Now, like I told you, we use black bodies to help us study and understand stars. This very first thing I talked about, it absorbs all electromagnetic radiation that strikes it, is not what we are going to be concerned with. We are going to be concerned with the second thing that a black body does, okay? And that's the second statement here, starting right here. The relative intensities of radiation at different wavelengths that it emits depend on the temperature. So this is the second thing. The light that a black body emits depends on the temperature of the black body. So let me rephrase that because that's not exactly what it says here, and I'm going to try and make it easier for you to understand. The frequency of light that a black body emits depends on the temperature of that black body. This is the aspect of a black body we are going to be concerned with stars, okay? The temperature of the star will dictate the frequency of light that is emitted by that star, okay? And so this is what we're talking about here. Stars closely approximate black bodies. This is why we use them to study stars. What aspect of a black body do stars approximately emulate? It's the second statement. The frequency of light that a black body emits depends on the star. The frequency of light, I'm sorry, let me rephrase that. The frequency of light that a black body emits depends on the temperature of the black body. Therefore, the frequencies of light that a star emits depends on the temperature of the star, okay? And so this is how we use it to study. The second statement, not the first one, the second one, okay? Now let's talk about a couple of the laws. Wien's law is the first radiation law that we're going to talk about. Wien's law states that the peak wavelength of radiation emitted by a black body is inversely proportional to the temperature. So again, we're talking inverse proportionality. So what does this mean? As the temperature goes down, the peak wavelength goes up. As the temperature goes up, the peak wavelength goes down. I'm going to show you a graph of exactly what this looks like here in a minute. But Wien's law states the peak wavelength of radiation emitted by a black body is inversely proportional to the temperature. So what does that mean about a star? That means the peak wavelength that a star emits is inversely proportional to the temperature of that star. All right? This is Wien's law. Next one, Stephen Boltzmann's law. The hotter the black body, the more radiation at every wavelength it emits. So the hotter the black body is, the more frequencies of light it will emit, okay? So what does that mean for a star? The hotter the star is, the more frequencies of light it will emit. Guys, black bodies and stars emulate each other in this way, okay? Okay, so I'm not really concerned about this last statement, so don't worry about it. I'm sorry I had to take a second to read it to see if it's even anything I want to discuss. It's not. I want you to understand what Wien's law says and what Stephen Boltzmann's law says. And the next graph, I believe, is going to show us, or the next PowerPoint slide is going to show us a graph that demonstrates Wien's law and demonstrates the Stephen Boltzmann's law. Okay? Both of these fly back to this second statement about the relative intensities of radiation at different wavelengths that it emits depends only on the temperature. Okay? So, let's get started on this. All right, so black body curves, guys. And again, this is demonstrating the laws. All right. This is demonstrating two things, okay? And again, let's go back and just take another quick look. The Stephen Boltzmann law says that the hotter an object is, the more radiation at different wavelengths it will emit, and the Wien's law states that the peak wavelength is inversely proportional to the temperature, okay? So first off, we're going to take a look at Wien's law with this one here. Whoops, sorry, I went the wrong direction. All right, so black body curves. Here we have the wavelength of light down here. Here we have the intensity, temperature, brightness, however you want to look at it, okay? So it states that Wien's law, that the more intensity, the higher the intensity of the black body, in other words, the hotter it is, the lower the wavelength of temperature of light will be. So if we take a look at three different, at a black body at three different temperatures, 3,000, 6,000, and 12,000, as you can see, the temperature of the black body is going up with each of these curves, okay? So if a black body has a temperature of 3,000 degrees Kelvin, these are the frequencies of light it will emit. That's Stephen Boltzmann's law. So it will emit this range of wavelengths of light, this range of frequencies of light. It will have a peak wavelength right there. This is what the mathematical model shows us. Now, if I increase the temperature of that black body to 6,000 degrees, it emits a much wider range of frequencies. This is Stephen Boltzmann's law. It got hotter, so the range of wavelengths of light emitted will increase. It also states that the hotter it is, the peak wavelength will become smaller. So it got hotter, it's now 6,000 degrees. There's the peak wavelength. It's there instead of there. So the wavelength got smaller the hotter it got. This is the Wien's law, okay? Now if I increase that black body temperature to 12,000 degrees, you'll notice that the range of frequencies it emits goes all the way off the chart. So it's way over here somewhere. Much wider range of frequencies emitted. Again, this is Stephen Boltzmann's law. The hotter it gets, the peak wavelength will become smaller. Here's the peak wavelength. You'll notice that's way over here. So the peak wavelength has gotten smaller. The range has gotten bigger. So this is how black bodies behave. This is what we call a black body curve, okay? Now, stars emulate this. So what we're going to do in the next slide is we're going to show you the temperature of a black body curve, and we're going to compare it to the sun's curve. What frequencies of range of light does it put out versus wavelength, and where is the peak wavelength of the sun at that temperature versus a black body, okay? So, the dotted line that you see here is the black body curve. This is the dotted wavelength for a black body that is 5,800 degrees Kelvin. Well, guys, if I'm going to compare the sun to this temperature of a black body, What do you think the temperature of the sun is? It's not difficult. I just gave it to you. The temperature of the sun is 5,800 degrees Kelvin. That's why we're intercomparing these two. Okay? So the dotted line again is the black body curve. This funky curve you see here that's got a lot of jaggeds in it, that's the sun's actual black body curve, okay, from the sun. You'll notice they match, okay? This is why we can use a black body to tell us information about a star. If I see a star, a brand new star we've discovered, and I know what its temperature is, I can simply look at a black body curve in the laboratory and it'll tell me everything I need to know about that star as far as peak wavelength, peak frequency, frequency range, so we can use black bodies to help us study stars in space. Okay, it gives us all kinds of great information. All right? Okay. All right, we're going to get into spectrums. Okay? Spectrums are produced by light. We know that the color of light can tell us relative temperatures of things, okay? Light can tell us, light we study using Wien's law and Stephen Boltzmann's law can tell us the frequency range of wavelengths coming out of a star, can tell us what the peak wavelength of being emitted from a star is. All this is coming from light. Spectra are also being produced from light from objects. We're talking astronomy, so we're talking stars, okay? This is what we call a solar spectrum. What do I mean by solar? This is the spectrum of the sun. Now you'll notice in this spectrum I've got red, orange, yellow, green, blue, indigo, and violet all the way across here. But the one thing you'll notice is it's got blank spaces in it. These blank spaces you see in here are the spectrum. A spectrum, ladies and gentlemen, is the fingerprint of an object. Each and every one of us has a fingerprint, and our fingerprint is not like anybody else's fingerprint, okay? This is what separates me from the rest of you in the class, is our fingerprints. Other than that, everything else is the same. It's our fingerprints, okay? Now, somewhere in this classroom, give me just a second to see if I can find it. And I cannot, someone has removed it. The chemical chart, y'all have seen it in school, okay? The periodic table of chemical elements. Each and every one of those chemical elements has a separate spectrum from the other ones. Hydrogen doesn't look like helium, doesn't look like lithium, doesn't look like boron, doesn't look like oxygen, and so forth, okay? So, each of those chemical elements has a unique spectrum, a unique fingerprint. Okay, combinations of those chemical elements, like water. Water is a combination of hydrogen and oxygen. When you look at the spectrum of hydrogen and oxygen put together to make water, it doesn't look like the hydrogen spectrum plus the oxygen spectrum put together. It looks completely different. Okay, so a spectrum is the unique fingerprint of an element or combinations of elements. They all have unique fingerprints, therefore unique spectrums, okay? Now, what can I tell from this solar spectrum right here? I can tell what it's made of based on where these lines are at. Because remember, each of these colors is a different frequency of light. So I can tell by where these blank spots are what frequencies of light are missing, and therefore from that I can tell what the star is made of, okay? Now, this is an example of a solar spectrum, and I'm going to explain how this is produced. But first off, we're going to talk about spectrums in general and what are the different kinds of spectrum, okay? I'm just going to do a real quick introduction. We're going to take a break, and then I'll come back and finish this. But there are three spectrums that we use in science and engineering. We have what we call the continuous spectrum. This is the most worthless. This is, for the most part, a training spectrum. We have what we call the absorption spectrum. And we have what we call the line or bright line or emission spectrum. Okay, the emission line spectrum. It's also called the bright line spectrum, okay? So we have three kinds: continuous, absorption, emission. Let's take a quick break. When I come back, I'm going to talk about how each of these are formed and how we use them.